right. Thanks. So in making inference and predictions about infections, the best situation is to have multi-annual time series data sets, historical and at multiple locations. And the best example that we have of this is measles in England and Wales with 70 years of case data. However, for unfamiliar infections, we have to broaden our inference toolbox to deal with only a few years of case data or indirect data sources. And then to use these standard inference tools, we have to have some knowledge of the internal structure of the model. So this model, the basic model structure, is a class of compartmental models, and it tracks the movement of individuals from susceptible to infected to recovered classes. Minimal information required is some knowledge of the infected individuals in a population and the bursts in a given population. And so the unfamiliar infection that we're interested in applying these models to is hand, foot, and mouth disease in Asia. So despite being a globally endemic, fairly benign childhood infection, the number of complicated cases leading to death has increased, and the main pathogen behind this is enterovirus 71, a relative of poliovirus. So we have relatively good data for this unfamiliar infection in Japan, case data through time and across space. Patterns of epidemics have been shown to be cyclical in Japan, occurring every 2 to 3 years. And note that there are two main patterns in this time series. First, there are large, severe peaks, and there are several smaller, messier peaks. So if we can capture these nonlinear dynamics of the infection, then we'll have a better chance of predicting the success of future control measures, like the vaccine that's currently in stage 3 of development. So we begin with a simple time series SIR model. The time steps match the infectious period. All the dynamics are captured within this 2-week period. And the model uses information of infections and bursts to reconstruct the susceptible population because we don't know it from firsthand. So applying the one step ahead TSIR to the Japan data, we find that the model fits the data fairly well, and it's driven by the strong seasonality and transmission. The data's in black and the model's in red. The problem, however, this model only predicts 2 weeks ahead. So we want to improve our predictive power from those 2 weeks to potentially multiple years ahead by employing some more sophisticated inference methods and also throwing some more computational power at the problem. And these methods have been published recently in the literature. So to do this, we're using tools developed as part of an online social modeling site, Simference. This project's still in development with my 2 colleagues at Princeton, Sebastian and John. And Simference is a platform for sharing and testing these complex models, providing cluster-ready code and more simplified processes to run this model. So this is the average result of one such method, particle filtering, applied to the Japan data. So the number of cases is in red, the noise around those cases is in green, and then the average model is in blue. And so we found a really good fit, but this time we have predictive power up to 4 years ahead. And so this is looking at model predictability. The green star is the starting point where we take our initial conditions, and the green line is the predictions of the model forward, and the red again is the data, and the black is the average fit. So we obtain a truly predictive out-of-sample forecast of the number of cases. So the green line extending beyond the data is our prediction into the future of what might happen with outbreaks. And notice that the starting conditions can greatly influence the quality of your prediction, meaning that we really need to get these nonlinearities correct. So we're then interested whether we can use indirect sources of data like Google Trends to make inferences about the infection dynamics. And this can be done either using the internal model structure or by verification against actual case data. And in this case, we have both options to really test these methods. So we see that the Google Trends map fairly closely to the actual data, but there are 2 peaks, 2008 and 2011, where the noise doesn't actually match the data. And so we need to test whether this can be pulled out by different modeling methods that we use with the case data. So the simple TSIR did not actually fit, so we use more sophisticated models in the Simference platform. The black line is the Google Trends, and the red line is the best model fit using a simplex method. And so the first peak, at least, we got to separate out with the model. So we then compare qualitative aspects of the model in the case versus the Google Trends data, and we find that seasonality is actually captured quite well with the Google model as compared to the case data. So the peak transmission is occurring in mid-June. But however, the periodicity between the 2 data sets is quite different. So periods with the highest amplitude are the strongest. And for case data, we have a strong 1 and a 3-year period, but in the Google data, we're only finding that 1-year period. So we're missing something of the dynamics in this infection. So we successfully capture the seasonality using the Google Trends, plus some more sophisticated inference methods, but we failed to capture this multi-annual cycling of the nonlinear dynamics. So it remains to be seen whether these indirect measures can really provide the resolution necessary, especially when we're dealing with something with nonlinear dynamics. But based on the case data, we do have some positive news that we can confidently say that hand, foot, and mouth disease appears to be SIR, which is really good news for vaccination, meaning that has a good chance of being successful. So I'd like to say thanks to everyone here and for John for organizing this event.